Hello. So way back near the beginning of the semester, we looked at a data set of marathon performances. And we use this data set to introduce the one-factor model. So the first part of this video, I'm going to go over that data again. And then in the second part of the video, we'll look at a random effects model. Okay, so this reads in the data. And this makes a plot. So on the horizontal axis, actually let's look at the data real quick. So head of DAT. The data are marathon performances. There's a column for the name of the runner, column for their age, a column for the actual marathon that they ran. So we have data from New York City Marathon, Chicago Marathon, and Boston Marathon. The year, we have data from 2018 and 2019. The date, the time that the runner ran. So in the first row, Jared Ward, who is a professional runner and, interestingly, also a statistician. He ran 130 minutes and 45 seconds in New York City Marathon 2019, which is a 2:10:45. And I also created another column called mar_year. So this is just I joined in a string the name of the marathon and the year, because we're going to put separate effects for each marathon of each year. So on the horizontal axis, I converted mar year to a numeric variable. So this is going to give a number between 1 and 6, because there are 6 specific marathon year combinations. I perturbed the horizontal by a small amount. Vertical axis is the time in minutes. Turn the axes off and then I'll add them back. Turn the X label off. Y label is time in minutes. When I add the horizontal axis back, I give the labels as the levels of mar year. So that's this. And then I turn the vertical axis back on. All right, so this is the plot. This is the same plot you saw before. If I zoom it, you can see all of the different marathons. So these are the 6 marathons. Okay. So the first model we fit was a factor model, which is marathon year. So that's a factor with 6 levels. And if we summarize that, we get this output. So see if you can tell which level it picked as the reference level. We could tell that by looking at which one is missing. So the one missing is Boston Marathon 2018. So that's the reference level. So this number, just to review the interpretation, this is the estimated expected finishing time for a runner at the Boston Marathon 2018. Boston Marathon 2019 is 4 minutes faster. Chicago Marathon 2018 is 6 minutes slower. Chicago 2019 is 1.8 minutes slower than Boston 2018. New York's even slower. Okay. So this was, we're not going to look at this very much, but these are the design matrix with the dummy variables for the covariates. This part of the analysis was just changing the reference level. So this, again, this doesn't change the model at all, but it changes the interpretation of the intercept. So this is the expected finish time at Chicago Marathon 2018 now. There's other ways you can look at that. One is to get rid of the intercept. If you do a -1 over here. So now we interpret these as the finish times at all 6 different races. And we fit another model with just marathon. Okay, so the story here is it's telling us that Boston Marathon is the fastest one because Chicago Marathon is 6 minutes slower and New York City Marathon is 11 minutes slower. Now, if you follow marathon running at all, this should seem a little bit strange to you because the Boston Marathon is considered to be a slow course, whereas the Chicago Marathon is considered to be a fast course. So it should seem a little strange that this analysis is telling us that Chicago Marathon is slower than the Boston Marathon. So what could be going on here? Now, if you're really a fan of running, then you probably also know that most of the runners in the Boston Marathon had to run a qualifying time to enter into the Boston Marathon. So it's probably true that the average runner who runs the Boston Marathon is better than the average runner who runs the Chicago Marathon. So what we really need to do in this analysis is to account for the differing abilities of the runners who run these various marathons. So that's what we're going to do in the next part of the video. Okay, so we know how to do this. We just need to fit a two-factor model that has both a factor for the runner and a factor for the marathon year. So we can do that with the LM function. So that's what M5 does. Time in minutes is still the response, but now we add full name as a factor. So if a runner appears twice in the data set, then our model will account for the effect of that level, that runner. But we also have MAR year in here, so we're going to simultaneously estimate the different effects of each marathon. So let's run that. And let's print out the summary. And okay, now this is a bit of a mess because there's lots and lots of runners in this data set. So let's see, we don't even get to see when we summarize the model the coefficients for MAR year. But they're there if we just reach the maximum printing value. So there's actually 431 more rows in this table. All right, so let's try to figure out how to get what we need. So summary M5 dollar coefficients, that is the R object that holds this table. So how many rows are in there? There's 631 rows. So if we just printed out this will print out the last 11 rows. So you can see it finished printing out the last few runners alphabetically, and then it prints out the marathon effects. So those are in the last 5 rows. So let's actually grab the last 5 fixed. I'm calling that fixed coefs. Okay, so now we can see that it picked, again, Chicago Marathon 2018 as the reference level. But now it's saying that the Boston Marathon is slower than the Chicago Marathon 2018. So Boston Marathon 2018 is 6.6 minutes slower than Chicago Marathon 2018. And Boston Marathon 2018 is 2.83 minutes slower than Chicago Marathon 2018. Chicago Marathon 2019 was faster than the 2018 version. And both the New York marathons are slower. And if you know anything about the New York Marathon is not a fast course. New York isn't particularly hilly, but in the course of the marathon, you cross over several bridges, and the bridges themselves are actually hilly. So this is actually considered to be a slow course compared to Chicago, which is almost completely flat. Okay, so we know how to do this. It's a bit messy because you have to fit so many coefficients, one for each runner in the data set. So what I'm going to go over now is how to do this with a random effects model. So one thing you might do instead is treat the marathon effects as fixed or non-random effects. We don't want to make any prior assumptions about how those effects are distributed. Also, it probably doesn't really matter what assumption we make about the marathon effects because there's only 6 of them. We're not going to be able to tell whether or not they come from a normal distribution. But it may make a difference for the runner effects. So the way we fit random effects models is using the LME4 package. So I'm going to load in that package. And the particular function that we use to fit a random effects model is called LMER. So here is the documentation for that function. So I'll just point out a couple things that we'll need to know. The first argument to LMER is a model formula. So in LM, it also takes a model formula as the first argument. But we need to have some way of specifying which effects we're going to treat as fixed and which we're going to treat as random. And the documentation for the argument formula tells us about that. Let me just read this. A two-sided linear formula object describing both the fixed effects and random effects part of the model, with the response on the left of the tilde operator, so that's the same as LM, and the terms separated by pluses, which is also the same as LM, on the right. Random effects are distinguished by vertical bars separating expression for design matrices from grouping factors. So this says something about how when we specify a random effect term, we have to use this vertical bar notation. So let me show you how that works. So I'm using the LMER function over here. This is my response to the left. I have 2 terms separated by a plus. The one I want to make random, I have to put in this notation. So I'm separating full name with a vertical bar from the number 1. What this means is that I want to have essentially a different intercept for each name in my data set. We can also specify the data set. So that's the object dat. You can see that here in the documentation. All right, so this will fit the model that we want. We do the summary. And now you see that it doesn't, this is the entire summary for M6. It doesn't print out the runner effects now. Now we'll see in a minute, we can get those, but it doesn't print them out by default when you summarize the model. So what does it print out? So there's a block here for the random effects. What this is saying is that, let's recall what the model says is that the runner effects are assumed to be normal, mean 0, with some variance parameter, called that sigma 1 squared. This is saying that it estimates that variance parameter to be 2081. It also prints out the square root of that variance parameter. So if this is sigma 1 squared, this is sigma 1. That's just convenience so that you can, usually the standard deviation parameter is easier to interpret. So this is saying that the runner abilities as a distribution has a standard deviation of 45 minutes, which seems about right. The next line here is the estimate of the residual variance. So that's what we called sigma 2 squared. That's 498.5. And residual standard deviation is just the square root of that, is 22.33. Down below, we have a table for the fixed effects, just like in the summary of an LM object. And again, this is telling us that Boston Marathon 2018 is slower than Chicago Marathon 2018. That's actually the slowest one in the data set. 2019 is a little bit slower than Chicago 2018. Chicago 2019 is a little faster, and both of the New Yorks are slower. So this gives us somewhat similar estimates for the fixed marathon effects. This one is a little bit smaller. If we look back up in the fixed effects model, it gave you 6.66, but pretty close. It also prints out a standard error for each of these coefficients and a t-statistic. It doesn't give you a p-value, but you can calculate that using the pt function. And this is telling us the correlation between the fixed effects. That's just printing those out again. One thing to note is sometimes when you switch from a fixed effects model to a random effects model, the standard errors for the estimates can change. Here, this is telling us that they don't actually change very much. So this is the standard error under the random effects model, and this is the standard error under the fixed effects model. So these are roughly the same. If you look through each of these, the random effects model coefficients have slightly smaller standard errors, but for all intents and purposes, these are practically the same. Now, the fixed effects model, it also gives us an estimate of the residual standard deviation. That number is 22.3, which is essentially the same as the estimate for the residual standard deviation in the random effects model. So a lot of the things about these two models are pretty much the same. Biggest difference is it gives us a slightly different estimate for the effect of Boston 2018. Okay, so we can extract the fixed effects from the random effects model. Remember, M6 is our random effects model. This just extracts those numbers from this column in case you need them. More interestingly, you can extract the random effects. So this is ranf is a function that extracts the random effects from a random effects model. And so here you have a table with all of the runners' names in alphabetical order and the estimate for the random effect for each of those runners. So negative number means it's a better runner. So see if we can find somebody who's really fast. Rod Corby is a very good runner. Okay. Now this ranf M6 is kind of a weird object. If you want to actually extract these numbers from that object, you have to, this is actually, ranf M6 is actually a list. You have to get the first element of the list, and the first element of the list is a data frame, and the first column are those actual numbers. So what we kind of want to check when we fit a random effects model is the distribution of the estimated random effects and see if they're close to normal. So let's do that. And this is the distribution of random effects. So the very best runners are on the left side. So these have the fastest, most negative coefficients, which means faster times. And then the slowest runners are on the right side. So this is telling us that the distribution of runner effects is actually right skewed, which kind of makes sense. It's much easier to be a very bad runner than a very good runner. So perhaps this assumption of normality for the runner effects is not so good. In this particular case, it didn't really hurt us in our estimates of the fixed effects because we got pretty much the same answer. But that's somewhat interesting. We had a hypothesis that the reason that the model that didn't account for runner effect was messing up the estimate of the Boston effect was that the runners at Boston were just better. So one interesting thing about the random effects models, we can actually extract the runner effects for the runners that ran in Boston. So that's what this next piece of code does. So I'm going to look at this data set, and I'm going to pull out the rows that correspond to performances at Boston Marathon. And then I'm going to pull out the names. So this grabs those rows from the data set and then grabs their names. So these are the names of runners who ran the Boston Marathon. And these are the unique values. Okay. And let me convert this to character. I think this does make a difference. So these are their names. There's 550 of them who ran at Boston. This is the mean of all those random effects. This should have mean 0. Now, if we just look at the Boston runners, the mean of the random effects is -6. So this number is essentially 0. -4 times 10 to the -11. So that's essentially 0. This is the mean of all the random effects. Actually, let me reiterate that point. Let's round this to 4 decimals. So that's essentially 0. Let's round this to 4 decimals. And that's -6.172. So it is true that the runners who ran at the Boston Marathon are higher abilities, meaning lower effects. And lastly, let's make a histogram of these. I think this is kind of interesting. So these are the histograms. On the left is the histograms for all the runners' random effects. On the right is the histograms for runners who ran at the Boston Marathon. And they're pretty much the same. The major differences come in the tail of the distribution. So if you look at the tail of this distribution, so these are the very slowest runners in the data set, that there's fewer very slow runners who ran Boston. So look, there's just 1 blip here, whereas there's 3 blips here. These bars are slightly higher than these bars. So these runners out here did not run at the Boston Marathon. Oh, one other thing I wanted to show you. If we look at the summary of our random effects model, it said that the Boston Marathon 2018 is about 4.8 minutes slower than Boston Marathon 2019. A little bit of recent history for you. This is a picture of the runners at Boston Marathon 2018. That day was actually extremely cold and rainy and windy. And Boston Marathon starts on the west side of Boston and runs into downtown. So it has a course that travels from the west to the east. In this particular year, there's a very strong wind, headwind coming from the east into the runners' faces. So this is kind of a historically slow Boston Marathon. And this over here, just for fun, this is Des Linden. She won the race and was the first American woman to win the Boston Marathon in a very long time. Okay, that's it for our random effects script. There's a ton more you can do with random effects. I wish we had time to go over all of it, but this is at least a little bit to get you started with the